So now in the analysis setting, here is number of steps. I'm going to use number of step as 200. So 200 substeps here, 200 sorry 200 steps are being created. So select all steps, auto time steps. I'm applying substeps, 250 substeps, and you need to turn on large deflection. By default, it will kept as off. You need to turn on this large deflection. One of the important thing to perform nonlinear analysis. Okay, now I'm going to apply a force at this midpoint, which we have already selected. So at y direction, that in the downward direction, so minus 5e power 6. So here, this is a step, this is a time, and you see this is step number 1 and this is also step number 1. What this is means step number 1 at a 0 second, step number 1 at 1 second. So step 1 at the starting time, at the end point, at the end time. So at the starting of step 1, 0 newtons of force is being added. So at the end of step 1, I want to add minus 25,000 newtons of force. So here, okay. Now I'm going to solve the problem. Now we are going to monitor force convergence. So till this gets completed, let me explain you what is a step and what is a substeps. So now, for an example, think as we have to apply 30 newtons of load. If it is applied in 3 number of steps, then 30 newtons divided by 3 equals to 10 newtons. So what it means is, at the first step we are applying 10 newtons. At the second step we are applying another 10 newtons. At the third step we are applying finally the last 10 newtons of loads. So at the first step, at the initial or beginning, the load is 0 newtons and gradually gets added up to 10 newtons. At the second step, the load start increasing from level newtons to 20 newtons. At third step, it is 21 newtons to 30 newtons. So I have also used substep in my analysis. So what is a substep? So if substep is used for each step, like for example, 10 substeps per step, that is one step equals to 10 substeps. What it means is to complete for one step, we have to complete 10 substeps. So for each substep, what is the load? We know one for one step. We know for this from this example, we know that for one step it is 10 newtons of force. So for each substep, how many newtons of force? So load is 10 newtons divided by 10 substeps. So 1 newton for each substep. So what it means is for the first step, so to complete a first step, one step, we need 10 substeps. So loads get added in 10 substeps. So for each substep, a load value is 1 newton. So loads get added like it starts for the first step, it starts at 0, slowly 1 newton a force gets added, which means one substep is completed. Like that, another substep 2 newtons, another substep 3 newtons, so on like that. At the 10th substep, we have 10 newtons of force. So 10 newtons of force at the 10th substeps. So 10th substeps meaning one step is completed. So our first step gets completed. For the second step, now same for the second step and the third step, we have 10 substeps. So at the second step, we are applying 10 substeps. Each substep has an 1 newton of force. So from 10, it's going to start. From 10, it's going to 11 newtons, which means one substep of second step is completed. So like that, so on, 10 substeps get added to give 20 newtons of force. So like that, cycle repeats for the third step, and the load slowly gets added from 21 to 30 newtons. What's the goal of these steps and substeps is to add the huge number of load at a regular interval of time, so that our load application looks like gradually applied load starting from 0 to our desired load. So this is 30 newtons of load, hence 3 steps. But in our case, our load is of 5 into 10 to the power of 6 newtons of load. So that 10 to the power of, sorry, for that 5 into 10 to the power of 6 newtons of load, I have divided into, I have divided it into 250, 200, sorry, 200 steps. So one more thing, 200 step end time is 200 seconds. So if you see time, it is 73, meaning 73 seconds has completed. This is pseudo time. That has nothing to do with your computational time or solving time. It is just a pseudo time. So 76 seconds has completed out of 200, which means almost a 40% of our work is completed. So now coming back to our problem. Since our problem has a 5 into 10 to the power of 6, a large amount of force, I'm not adding this huge amount of force in a single step. Rather, I'm adding these steps in a multiple steps, that to 200 steps. I have choose 200 steps. So for each step, it is 25,000 newtons. So when first step get completed, it is 25,000 newtons of force is being added to that cantilever beam. So I also have chosen substeps. I have taken substeps in our analysis. So substeps, if you have see 250, 250 substeps I have taken, 250 substeps. So if you divide 25,000 newtons of force divided by 250 substeps, for each steps we get 100 newtons. So so in my scenario, in this case, I'm applying a load of 5 into 10 to the power of 6 into multiple step, that too in substeps. So for I'm applying slowly from 0 to 100, 100 to 200, 300, 400, like that. At 25,000, after applying 250 substeps, one steps get completed. At that one step, our load value will be 25,000 newtons of force is being applied to our problem. And then our problem shifts to second step, same 250 substeps, same 100 newtons of force incrementing. So at the end of the second step, we'll reach 50,000 newtons of force. S- Again, same for 3 step. Again, cycle repeats up to the load of 5 into 10 to the power of 6 newtons of load is being added. So if you see here, I have set it to force convergence. Now if you see here, blue line indicates load substeps. Load step converged. So this is first load step, second load step, third load step, so on. Like that we have, 200 load steps. Load steps, step. On that step, our given load is converged. So hence that. So this is step number one. This first blue line indicates step number one. Second blue line indicates step number two. On that particular line, our load, whatever the value at that step, that load is converged, and so on. Now, so here at the first blue line, we successfully added 25,000 newtons of force to our problem, and so on. It's being adding the load slowly such that it reaches till 10 to the 5 into 10 to the power of 6 newtons of force. Almost 70% is completed. Hmm. So this is a nonlinear analysis, hence that is the reason it's taking almost 10 to 20 minutes. I have also used 200 steps, and if you would do the same analysis by using a solid model of cantilever beam, you might need hours of time to solve this particular solution, or maybe days. If you use coarser mesh, if you reduce the number of steps and the substeps, but since I have taken a line element, I have increased number of steps and I have increased substeps. So I think it approximately take 10 to 15 minutes of time to solve it. You can also choose to go with lesser steps, lesser substeps, but since this is a line element, I am simply increased that much. And for simplicity, we have taken a line element. If you see here under a mesh, if you go to statistics, sorry, if you go to statistics, here you see 980 elements. You see exactly 980 elements. But if you have gone with 3D model of a cantilever beam, you would have get all. If you have used a fine mesh, you would have ended up with something around 30,000 to 50,000 of element, and double that, double the nodes. So the computational, that's hence the reason the computational resources will increase and the solving time will increase, because it is easier to solve 980 elements to get a result rather than solving 30,000 to 50,000 elements to solve and getting a result. So hence the reason I have used a line element, so that we can simply use lesser resources, computational resources, lesser solving time, and get the same accurate result as we would have used with solid modeling of cantilever beam. So our solution has completed. You see here our solution has completed. So now at here I'm applying directional stress about y-axis, apply a result. So this is the 0, here is 0, here it is a maximum. That's the directional. Now here if you see the stresses and strains are not available to us, that is because in the solution, in the solution we need to turn on this beam section results, because we have used a line element which is representing a beam. In our case, a propped cantilever beam. Here we need to turn on this and then evaluate results. Now now our line element behave like a beam and will give us the result of a beam. So anyone doing a simulation for nonlinear analysis using a beam or line element, for beam using a line element, uh, before solving, you make sure this beams section results is kept at yes. So now we have stresses and strains. So stress, let me apply a stress, strain, maximum principle. Here we have equivalent plastic strain. Equivalent plastic strain is not available to us. So okay, this is equivalent stress. Now evaluate the results. So after evaluating stress and strains, here it is a stress. So now this end is a fixed end. So if you look at the fixed end, this is the stress distribution and this is the hinged support. Now if you look at hinged support, this is the stress. Now here, exactly at here, we have point load. Hence the stress here is a maximum. So if you look at plastic strain, this is elastic strain. This is elastic strain, and plastic strain is is not available. So what you can do, you use user defined results. Here you need to put expression for plastic strain. So you will get that here. You need mechanical help. So you'll be at ANSYS help. If you go results, here you have user defined results. Okay. Here, this is an expression. Element nodal equivalent plastic strain as calculated by the solver. So we need to use this as an expression. Now expression, and it is a strain, and if you evaluate this result, so here we have an error. So warning here that equivalent plastic strain results were not calculated for some elements. Element equivalent strains are not currently supported for line elements. So I'm using ANSYS 19.2 version. So in this version, equivalent strains are not supported for line elements. So if you are using latest version, or if you're using newer version then 19.2, I hope you will find plastic strain for the line element. So this is how you need, if any result is unavailable, you can use it. So this is the nonlinear analysis of prop to cantilever beam. In fact, this is a simpler one for nonlinear analysis. If you have the complex, there are, when you deal with assemblies, different components together for nonlinear analysis, those problem gets more complicated, more solving power you would require, more solving time. So comparing to that, this we have only one component. So, so this is a simple nonlinear analysis. If we have multiple components, then the problem will get more complicated, and you have to use different settings, nonlinear contacts. You have to give, you have to use substeps, number of steps. You have to even use more steps or more number of substeps. You would require more large amount of computational resources to get complete a complex nonlinear analysis. So thank you very much for watching this video.